Coming up on Garden Talk.
There is so many different chemical constituents that plants construct to manipulate their environment in soil, whether it be the biological populations, whether it be pH in the rhizosphere. All of these things are all part of it. Overwatering can look like so many different things. And what's happening is you're creating an environment in where bacteria that isn't conducive to the health of your plant is able to colonize and grow. A lot of the bacillus species, they have the ability to encapsulate their DNA into an endospore, and those endospores, they create like a wax coating. They're really resilient. There are so many products out there that are so overpriced or have such small colony forming units that they're going to be ineffective.
What's up, everybody? If you that don't know me, my name is Chris, aka Mr. Grow It, and you're tuned into the Garden Talk podcast. This is episode number 16. In this episode, I interview Brandon Rust. He is the owner of Bokashi Earthworks, which is a biological fertilizer company that specializes in microbial inoculants. He has been cultivating for 20 years, and he currently owns a 40-acre farm in Oklahoma. Great episode that I have for you today. This is more of an advanced discussion where we talk all about microbes. Some of the things that we talk about in this episode are ideal soil temperature for microbe activity. We talk about large swings that can happen in the microbe population, the rate of microbe reproduction, and a whole lot more. Click the thumbs up button and subscribe to the channel if you haven't already. If you're listening to this podcast on one of the podcast platforms such as Apple Podcasts, please leave a rating and review. And a big thank you to those of you that support this podcast on Patreon. If you would like to directly support this podcast, you can do it through Patreon. The link to that is patreon.com/MrGrowIt. I'll also link it down in the YouTube description section below. Before we get into the episode, I'd like to give a quick shout out to our sponsor, Happy Hydro. Happy Hydro is giving away a Chilled Tech GrowCraft X6 LED grow light. All you have to do to enter the giveaway is to click the link in the video's description section, which will take you to Gleam. Gleam is a giveaway website that tracks the entries. When you get there, you'll be able to enter the giveaway by visiting the Happy Hydro YouTube channel, and then while you're there, click the subscribe button, and that's it. You're then entered to win the Chilled Tech GrowCraft X6 LED grow light. Good luck. Now let's get into the episode. All right, here we are. Brandon Rust, welcome to the Garden Talk podcast. How are you today?
I am wonderful. Busy as always, but happy to be on another podcast and spreading the information that I've accumulated over the last 20 years of cultivating.
Yeah, I'm super stoked to have you on here. I've seen you on so many different shows. I mean, before we hit the record button, you had mentioned you're on over 100 different shows or podcasts, live streams, whatever, which is awesome. And the amount of information you give to the community here is extensive. So first off, thank you so much for doing that service, because you've been helping out hundreds of thousands of people, if not millions of people, throughout all these videos and so on and so forth. So thank you for that. Now, for the people who, there's got to be some people in the audience here that don't know who you are. So can you introduce yourself, tell us a little bit about yourself and how you got into gardening?
Sure. My name is Brandon Rust. I'm from San Diego, but I currently reside in Oklahoma. I started cultivating medicinal plants 20 years ago. I was a teenager, 18, 19 years old, and I had some older guys show me how to cultivate. Back then we were doing hydroponics. I've since moved to doing living organic systems. And if you guys are interested in any of the work that I do, you can find me at rust.brandon. And you can find, links there to my company, Bokashi Earthworks, which is a biological fertilizer company. I specialize in microbial inoculants for nutrient cycling, soil health and fertility, and integrated pest management. And then I also own a 40-acre farm out here in Oklahoma with my partners.
Awesome. And then I actually Googled your name before we met up today, and I think the third link down, if you Google his name, Brandon Rust, the third link down goes to Herbage Mag, and there's actually a written article about you, kind of your story. So if anybody's watching this wants to learn the next level down about his journey here over the past 20 years, it's definitely a good read. It's only about a page long, so but definitely worth the read for sure. Cool. So I think it's appropriate to just start with the soil food web. That's actually something that hasn't been discussed yet on my Garden Talk podcast off of any of the guests. So let's start with that. Maybe if you can take, roughly 5 minutes or however long it takes to kind of talk to us about what the food web is in somewhat a basic or beginner friendly type way.
Sure, I'm sure that most of your viewers are familiar with, the food web. It's something that we got to see in elementary school, what eats what's higher up in the food chain. Soil food web is that same exact thing for the soil and the species that interact, the way that they, release mineral nutrients. And it's basically just the diversity of different types of microorganisms, micro and mesofauna, and then macro flora and fauna, as well as arthropods, earthworms. So, it's complicated, but really it's not. It's basically just that there are certain things that do certain things in the soil, and they feed off of each other. They work, synergistically and symbiotically with each other. Basically, it is the web of life that perpetuates life.
And that's what we're going to be talking all about microbes today. So we're going to talk about the biology. We are going to definitely get into a little bit of chemistry here, which is, warn everybody, I'm a beginner when it comes to chemistry. So some of the stuff actually might go over my head, which it might go over some of my audience head as well. But it's okay because we can always look back. We can always do additional research and so on and so forth. So
it goes over my head. I consider myself a really intelligent person. I read tons of white papers. I read literature all the time. The complexity of these systems is, to be able to really have a firm understanding, you have to have a really good imagination.
Yeah, absolutely. So chemistry, and then you get into like biochemistry, and then you get into, we might even touch on
mechanics.
Yep. So much. It's endless almost.
It really is. And that's one of the reasons that, soil science is so intriguing, is because there will never be a point where I come and say, oh, I can't learn anymore. Yep. It'll always be a journey. So I'm just taking people along with me as I go.
And that's what makes it fun, for sure. So a lot of my audience does use synthetic fertilizers, right? Synthetic nutrients. Yeah. And we often hear about salt buildup resulting in problems. Now, when we're talking about salt, we're not talking about sodium chloride, right? The table salt. So what exactly is salt from like a chemistry standpoint?
Well, when we're looking at, typically when we are looking at these systems in soil anyway, we are looking at chloride and sodium Na. What happens is there are certain chemicals that are biologically available for the plants to utilize for the specific functions, whatever they may be for. In these natural systems, you have what's called oxidation and redox potentials. And essentially, certain elements are biologically available, and we see this like in pH, right? But there's more to it. We see it in pH, and that is going to be certain things are available. There's a bigger picture to that. And typically when you're using synthetics, they're taking a chemical that can be absorbed by a plant, but it's also in a chemical formulation to where it's not going to be affected by the oxidation and redox potentials of those systems. So inherently, you have kind of you have two systems, right? These organic systems, which, we still use things like mineral salts, but they're not synthetically created, right? The ones when you can get the same effect with either. But what happens is with synthetic fertilizers, you're accumulating a lot of chemical compounds that are going to interfere and have antagonistic relationships with what you're trying to absorb, right? And also, oftentimes these chemicals are in such high quantity that they are grossly over applied. When you grossly over apply a synthetic fertilizer, it can adversely affect the biology of that soil, but it can also affect the abiotic nature of that soil, which is anything that's not related, all the different stress factors that could be that aren't related with biology. So like the weathering, when you have those types of chemicals, they can tie up soil, they can tie up nutrient, they can cause anaerobic conditions when they dry out really easier. They don't hold moisture as well. So you have different conditions that eventually accumulate. And it's not to say that this can't happen also in organic systems, because it totally can. You can accumulate things like chloride and sodium in these in organic systems as well. And they'll compile, and again, what it does is causes antagonistic relationships. It hinders microbiology from being able to procreate and reproduce. And it also comes at a great cost to environment in the production of those chemicals.
Gotcha. Now, I guess one of the ways that I was kind of explained to try to make it a little bit simpler terms, I guess you could say, is, when you have these bulk nutrients, you're mixing it with water, it's somewhat like binding to that H2O. It's going into the soil, right? And then the plant is uptaking it, or it's staying there and the water's evaporating, and then you have what's left over as an ion, I believe, and then that ion isn't available to be uptaken by the plant. Mm-hmm. And so my question is, are microbes able to access that ion at that point and eat that ion, or how does that work?
So when you have a large accumulation of antagonistic cations in your soil, it's going to make it so the plant can't absorb that. Bacteria, microorganisms, fungi, yeast, they all have amazing abilities to break down almost anything that is a hydrocarbon compound. So if it is, I guess anything in organic chemistry, because I guess organic chemistry doesn't necessarily have to be natural in nature. They can be synthetics, but when we're talking about organic chemistry, we're talking about anything that is a hydrocarbon compound. That being said, there is a microbe for every compound, because the amount of microbes that we have vary in such a huge species of diversity. And when we're thinking about, at least when I'm thinking about microbes, I'm thinking of it kind of like varieties of medicinal plants. Some will have a lot of different effects, right? Because of the metabolites that they're producing, or the chemical constituents that those plants produce. Microorganisms are very similar in that they all produce different chemical constituents. Some of these are their secondary metabolites, just like the plants produce. So what we'll see is there are some bacteria like phosphorus solubilizing bacteria. They release an enzyme that's able to release phosphate, the only plant available source of phosphorus, from inorganic mineral compounds, from rocks, from things like calcium phosphate or calcium bentonite or wollastonite. There's so many different types of calcium, and when we're looking at calcium as a chemical, we're not just looking at Ca, right? It's always attached to something like CaSiO, calcium silica, or calcium phosphate, or calcium silicate. a lot of these elements that we use in organic farming are usually attached to something else. All of the mineral sulfates, it is a mineral, it is considered a salt, right? Because it's soluble in water. So you can take almost across the board, there is something for an organic situation if you need to make up for a deficit that is immediately available. And I know that's, I've heard people say, oh, you can't get things immediately in organics, and that's absolutely not true. There's a difference between what you're putting in, right? If you're using a mineral salt, an organic mineral salt, you can do the same thing. You can hamper a system the same way you could by over application in a chemical system as well. But when you're using something like a meal, anything that has a meal attached to it, whether it's feather meal, bone meal, kelp meal, those are all things that biology is going to have to utilize to break down to release into the system. Anything that has a sulfate on the end of it, potassium sulfate, iron sulfate, zinc sulfate, these are all mined minerals that come out of deposits, whether it was like in a volcanic eruption, a natural seabed mine that dried out, a rock quarry. They're mined mineral sulfates, but they're water soluble, or they have more solubility in water. Now, they don't all have the same solubility, right? Magnesium sulfate, aka Epsom salt, has a way higher solubility than, let's say, calcium sulfate or gypsum. We're talking about a huge difference. So, when we're talking about salts, we're talking about things that are soluble in water, which you have to be careful of too, because we're usually talking about a cation. And there's four, but there's three cations that we're looking at specifically for, when we're farming. And that's calcium, magnesium, and potassium. There's also sodium, Na, but that's antagonistic to all three of those. So we want sodium to always be as low as possible because it is a salt, it's a cation, and it's antagonistic, and it'll cause blockout or lockout. Even if you have adequate amounts of everything you need in your soil, let's say your soil is perfectly healthy and balanced. Well, I guess it wouldn't be balanced if your sodium was up. But let's say everything else was good, but your sodium is really high. What is mostly going to be affected are those major cations, the thing the plant relies on for the majority of its biomechanical processes.
Gotcha. That's very interesting stuff there for sure. Now, in some organic gardening books, it's mentioned that feeding synthetic nutrients are going to kill off the microbes. However, on online sources, like there's this gardening myth website, it says that that's completely false. Feeding in synthetic nutrients, you're actually feeding the microbes. So is it true that feeding synthetic nutrients are going to kill off the microbes? If so, how fast do the microbe populations die off when feeding these synthetic nutrients?
Well, so I don't have any actual data that's going to say this is exactly what is happening. And, I'm a data-driven cultivator. That's how I do all of my agronomy. I look at what's in the soil and stuff. When it comes to biology is it's pretty resilient. A lot of these species have the ability to endosporulate, which encapsulates their DNA, and they can survive in extreme conditions, whether it's high or low pH ranges, high and low temperature ranges, and all different types of abiotic and biotic stress factors. That being said, it does hinder biology when you're using a bunch of, again, you're talking about an organism's inability to use what it needs. What people don't understand is that bacteria, microorganisms are very similar to plants. I mean, plants wouldn't exist if it wasn't for the relationships that they co-evolved with the different microorganisms. And the microorganisms also require a diet, right? It's not just nitrogen and calcium, right? They need iron, they need manganese, they need a lot of the same elements that plants need. And again, if you go and throw a bunch of stuff into a system that's not balanced, it's not just a plant that's going to be adversely affected. It's going to be the biology of those systems. How can they sequester any type of nutrient if it's just downright not available because there's this antagonistic relationship going on? Does that make sense?
Gotcha. Yep.
So not only that, but from my perspective and from, what I've seen, there are certain species of microbes that can tolerate those high salinity, high saline types of conditions. But because microorganisms are so fragile, which is kind of like, some species will be able to survive those types of conditions. What are they? Well, you have to do your research. We know that certain species of bacillus bacteria can still function really well in high salinity conditions. We know that there are certain strains of trichoderma that do this. There's like microbes for fucking everything. But when we're talking about specific microbes that we're utilizing in agriculture for a specific reason, whether it's for their production of selective target antibodies, or whether it's because we're looking for an enzyme production that they produce, we'll eliminate that because we need to have conditions where we can promote the types of microorganisms that are going to best benefit that species of plant in the environment that it's in.
Gotcha. That makes sense. And kind of piggybacking off of that, talking about getting into like large swings in micropopulation, that's never a good thing, right? Generally they say that if you're flushing your plant, for example, you could be flushing out a lot of those microbes. If you're over fertilizing, you could be killing, you could have that large swing in the population. Large pH fluctuations is another thing that I've heard could potentially hinder. You could have a large swing in the micropopulation
Absolutely.
as well. Are there anything else or talk about that stuff a little bit?
So temperature, pH, hydrology, those are going to be your three main components when it comes to which type of microorganisms are abundant in soil, but also plant species and what kind of photosynthase are they releasing into the soil? What type of exudate? Because when we're talking about plant exudates, there's the science that's going to come out on this is going to be fucking insane, dude. There is so many different chemical constituents that plants construct to manipulate their environment in soil, whether it be the biological populations, whether it be pH in the rhizosphere. All of these things are all part of it. If you go too low on pH, some species will completely die off. If you go too high, if you overwater and it goes anaerobic and you don't have the proper biology to start with, you could say goodbye. When we're talking about explosive populations, let's say that your plant's struggling a little bit, right? And you're like, oh, I can't figure out what it is. I see this all the time. Just from overwatering can look like so many different things. And what's happening is you're creating an environment in where bacteria that isn't conducive to the health of your plant is able to colonize and grow. So let's say that this is kind of like the beginning, right? You have this thing happening, you didn't catch it, and then you go and like you think it's a nitrogen deficiency. So you go hit these things with a bunch of amino acids, right? Like soy hydrolysate. What you're going to end up doing is you're going to compile the problem that you have because you just added a complex carbohydrate to a living soil system where the predominant microbe is something that's going to kill your plant. And you just gave them something that they love. So it's those types of, I guess, scenarios that biology can make a huge difference. Let's say you have a flat full of clones that you're rooting, right? And you overwater them and they become waterlogged, right? And all of those roots become anaerobic. Man, how long is it going to take for you to recover with that? And then let's say you go ahead and plant those things and you're like, oh, again, they need this or that. And you try to add something to the system and it throws it further to the left and not where it needs to be. You know what I mean?
Yep, absolutely. Let's move on to pH up and pH down. So I get so many comments in my comment section with a lot of people really scared to adjust the pH. pH down, for example, a common thing that's used for that is phosphoric acid. pH up, for example, a common thing that's used is potassium hydroxide, potassium carbonate. The common thing that's said is if we're using these things, we're killing off the microbes in the medium. Are we eradicating the microbes in the medium from a few drops or a few milliliters of, potassium hydroxide, potassium carbonate, phosphoric acid? If so, if so, do we know what the impact is on that?
Well, because one of those three things that I said earlier was pH. Large pH fluctuations are going to definitely affect the biology in the soil or what species can, exist. But if you're like, if your soil is at like 6.3 and you're like, oh, I want to get it up to 6.8 and you use, first of all, you're not going to be able to do that by pHing your water. Right. So pHing for water is usually done for hydroponics. Typically with organic growers, they are already starting off with a good source of water that's not high in sodium or bicarbonates. And if you're running hydro, there's some cases where biology might be important. Like maybe if you're doing a cocoa system, where those are going to be a little more conducive to biology, but you're not looking for like biodiversity in these types of hydro systems, right? Because if that was the case, then why are you even using synthetics in the first place? Microbes don't work as well in synthetic systems as they do in organic living systems. So that being said, if you're, running like cocoa or a hydroponic system where you're having to adjust pH and you're worried about biology, you're probably you need to be looking at specific types of microorganisms that can help that particular system out that aren't going to be affected by those types of swings. As far as pH in soil, typically, if you're using a good clean source of water that's low in bicarbonate and sodium and chloride, you shouldn't have to really worry too much about your pH as long as the soil pH is where it needs to be. Because the soil will buffer the pH of the water as long as the water is clean. If you have a bunch of bicarbonate in there and you keep adding that in, it's going to slowly raise that pH up. Not only that, but it's going to antagonize your cation balance and the ability for calcium, magnesium, and potassium, as well as even your other cations for your micronutrients, which is going to be copper, zinc, iron, manganese. The only one that's not a cation, I think, is boron. And, some of the other ones that I didn't mention, but out of those ones, out of the five major ones, major micronutrients that are responsible for a lot of the enzymatic processes, folding of proteins and RNA, and the biomechanics.
I think the concern for some of the folks that are growing in soil is that they're starting with a water source that's like a 7.5 or an 8.0 pH, and they're worried that that would have an impact. And so adding in that few drops, 2-3 drops of phosphoric acid to get that, pH down, they worry about that. So that's why I bring up that question.
Okay.
And then just kind of touching on organic pH adjusters versus synthetic. So we talked about like phosphoric acid for pH down, and then potassium hydroxide and potassium carbonate for pH up.
Well,
now, some people...
Okay, since you're mentioning those particular chemicals, right? Phosphoric acid and potassium hydroxide. Okay, so a lot of people who probably are using organic or who think they're growing organically, there is a lot of these. So those aren't organic chemicals, but they are used consistently across the board in a number of products. Anything from like nectar of the gods, those types of products where they're a liquid nutrient. What typically they'll do, they'll take something like bone meal and they'll dissolve it in the phosphoric acid. And so they're using an inorganic process to release organic substances that'll stay in a solution. Same with potassium products. There are potassium products that are labeled as organics, but they've been... So that's one of the things. Those types of things in small amounts don't hinder biology. It's those huge swings. And then also, if you're a home grower and your pH is high, go and test your water and see why it's high. Because typically that means you have bicarbonates and sodium in your water. Okay, so and if that's the case, you should be using a filter or using distilled water, or you should be... What happens in the systems is things can go fine for a really long time, but you compile problems slowly. It's why I tell people you shouldn't be I know a lot of organic growers. I was one of them that used kelp meal constantly and ocean inputs. And it's like, after you compile all of these things over run after run, dude, your sodium and your chloride are fucking skyrocketed. It comes from the ocean. Let's think about this for a second. Like, the ocean is full of fucking salt. So, not only that, but you have to remember too, heavy metals can compile the same way. So even if something has a small amount of heavy metals, but you use it consistently, it'll build up over time.
So when some growers are saying you should be using baking soda for a pH up versus, potassium hydroxide or potassium carbonate, or using lemon juice or vinegar for pH down instead of phosphoric acid, would you agree with that? Would you?
Dude, it's the amount that you're applying for that. Like, okay, so let's say I got a 50-gallon reservoir, right? And I need to take it down by 0.8. The amount of whatever I am adding in there is just not going to be enough to really like mess that up. It's when you have these wide fluctuations, when you have way overwatering and then way too much dryback, and it's consistency is kind of key. That's why the blue mat systems work so well. If you have something that's consistent all the time, you know what to expect.
I love blue mats. I actually just started using them, and they're awesome. So good. So one thing I learned I think you touched upon it, is that different microbes are going to function best at kind of different pH values. Is this true? And then
Yeah.
kind of what is that ideal pH range, for soil and I guess for hydro that people should kind of stick with?
So here's the thing, right? The soil pH range that it's such a weird thing to address, because there's an optimal range for soilless media, and then there's an optimal range for medicinal plants. But the ranges for pH for different types of bacteria, different microorganisms, is all over the place depending on species, right? It's like typically all plants on Earth are between 5.5 and like 8 at the highest, usually. I mean, depending on the type of soil that they're in, but blueberries are something that is acidic. They like acidic soils, and there's other plants that like a little more calcareous soils, or higher pH soils. You can say that about plants. You can't say that about microorganisms, because there are microorganisms that prefer to have an incredibly low pH range. Well, there's some that will only function in a high pH range. There are some microorganisms that will not function at all in the presence of oxygen. There's some that are facultative. They can function in high or low. And there's some that only function in high oxygen environments. Microorganisms are so abundant, and they have so many different ranges. But what I'm looking at for the types of microbes that I use, it depends on what I'm trying to do with it. This product right here from my company, Bokashi Earthworks, which is a consortium of several different bacillus species, non-purple sulfur bacteria, right up Pseudomonas plustrius, and also yeast, which is Saccharomyces cerevisiae, also known as brewer's yeast. That yeast is very common. It's found in soils. It's found on fruit. For this particular product, if the pH doesn't go below 4.5, it won't stabilize. So for this specific consortium, although they can operate in a wide pH range from like 3.5 all the way to like 8.5, if I want them to do a certain thing and have viable spore, it has to be at a certain pH, right? So where they're suspended in solution, they're all alive, and they're waiting for the opportune environment to where they start procreating. Microorganisms are very strange like this. Small things can change what's going on. We also know that there are certain microorganisms that we can't even, we can't culture in laboratory settings. They only exist in nature, and they can't be grown and cultured because their nutrient requirements. Think about it like this. If you had a medicinal plant that had this really crazy, wild nutritional need, and it was not typical to what you usually want, and it's just all over the place, and you would have to figure out exactly what this is, and it was only this one special mix that you would never find anywhere else for any other plant in the world, is the only thing that would make this thing grow. It's how it is for some of these microorganisms in these biological systems. Some of them will only exist while a certain species of plant is present, and it's giving, and that plant is releasing a photosynthate and exudate into the soil that's going to sustain the nutritional needs of that specific microorganism.
Gotcha. Good information there for sure. So let's talk about kind of the soil temperature in a sense. So one thing I've learned is that the lower the soil temperature in the medium, the slower microbes move. That being said, what is the ideal soil temperature for microbial activity?
You'd be surprised, it's 84 to 98 degrees
Wow.
for most species. You know what's really interesting? When you increase your VPD and you're running high temps, high humidity in soil systems, you get way better nutrient cycling capacity. Your phosphorus is gonna cycle better. So will some other things. This is what I've seen from data that I've collected, right? And it's like this. This is why. When you think, at least when I think of how to culture a microorganism, you have certain environmental factors. Microbial incubators are typically used to culture different types of spore. And those ranges are usually between 84 and 98 degrees, depending on the species and the bacteria or fungi, whatever it is that you're culturing. Now, there are different species that do better at higher, lower temperatures, like we talked about earlier, higher, lower humidity. But what I've seen in soil is that when you have higher temperature, higher humidity, everything works better as far as nutrient cycling capacity. When you're seeing how things fall into solution, especially for phosphorus. So yeah, soil temperature. We got cut off for a second, but so I'm looking at things from how do you grow microbes, and usually you're looking at higher humidities, higher temperatures. And the same thing applies in these systems. When you have the higher humidity and the higher temperature, you're able to retain more moisture as long as you have a really, for these modified soil mixes that most of us organic growers are using, they're highly porous. So that maximizes the gas exchange capacity of that soil, which means there's a lot of oxygen. It's able to retain the moisture while still having a lot of oxygen and have those higher temps. It allows for these populations of microbes to really cycle. It just increases their activity. You can kind of see this too if you go and say you mixed up some fresh compost and some amendments, maybe some alfalfa, stuff like that. And when you put it into your tote, to cook, you get the mycelium, you get all the bacterial and fungal growth, all the mycelium mats, and it's because you have those nice warm conditions. When everything starts to cycle, right? When there's a lot of food for them to sequester and there's a lot of things to be broken down, there's plenty of carbon, plenty of nutrient, those environments usually warm up. And it's because of all the activity. They can get too hot, obviously. We've seen that with thermophilic compost, where it gets too hot. I've actually seen compost light on fire before. But yeah, those temperature ranges seem to do better with the higher humidity and higher temperature ranges. Obviously, when we're growing a medicinal plant, we don't usually want to exceed a leaf temperature of 84 degrees, unless you're able to, really maximize that environmental condition where your nutrients are all on, they're sufficient and balanced, and then you also have supplemental CO2, your VPD is in range. If you go higher than those temperatures, it has a hard time with some of the enzyme mechanics of photosynthesis, or not photosynthesis, but with the creation of chlorophyll, and you really have to have everything dialed in if you want to, maximize that. But ideal range, man, if you can run your VPD a little bit higher without going over and kind of keep your humidity up, but consistent, because one of the things that will cause bacteria to grow, bud mold particularly, is if you have huge fluctuations. Again, it's those fluctuations from where your consistent VPD and it either drops or it goes too high. Consistency is kind of key, is what I've seen. As long as you have consistency across the board, things seem to function pretty well.
Gotcha. Yeah, because soil temp isn't something really that a lot of people talk about. Since the soil temp has such an impact on microbial activity, should we be monitoring it more closely? Like, would you consider the soil temp just as important, or even more important than the canopy or leaf surface temperature?
It's a really good question, and it's not something that I've really done a lot of science on. I haven't really delved into what's happening at different temperatures. I haven't even really taken soil temperatures, to be honest. So it's something that it piques my interest, definitely. And it's another data point that could be taken into consideration while we're looking at things like the soil test, saturated paste test, the leaf tissue, and the sap testing. How is soil temperature affecting things? I'm usually not looking at soil temperature. I'm usually looking at RH and temperature, and those are the things that I'm mostly looking at. Surface temp on the leaf if we're using LEDs. LEDs are a little bit more complicated, in my opinion.
Gotcha. Okay. So switching up a little bit. So general question here. When the soil dries out, microbes go dormant, right? It's kind of like a sleep state for them. Do some actually die at that point if the soil dries out, or no? Or like when you rehydrate it, kind of they wake back up from that dormant state?
Yeah, so there are different microorganisms that are going to be ubiquitous to the environment. They're all around us. Those types of microorganisms will reestablish themselves. However, if there was like a specific microorganism in that system, it could potentially be eliminated unless it has the ability to endosporulate, like we talked about earlier. So some varieties, a lot of the bacillus species, they have the ability to encapsulate their DNA into an endospore, and those endospores, they create like a wax coating. They're really resilient to different type of biotic and abiotic stress factors, and that's what makes them such a prevalent species in soil. And so when they do dry out, if you have large microbial populations, what will happen is you'll have a lot of tiny little microorganisms that create these wax coatings, and that's what causes soil to go hydrophobic. So if you've ever seen a really dry soil, you pick it up, throw it on water, it floats. It has to completely rehydrate until that soil will actually sink, and it's because, and so it's the same thing. Same thing could happen. That's really what you are going to be more concerned about, because you can always re-inoculate, or those populations are going to naturally come back once you rehydrate that material. The problem is it can be really difficult to rehydrate soil that's gone hydrophobic, and oftentimes it takes something like a surfactant, so you can get that penetration into dry spots. So that is really the main concern with letting your soil dry out. But yeah, it'll come back. There are microbes in that soil. They will continue to be there. Some of them will die out. Here's an example, right? Anything that's going to be like an anaerobic species, which is most of your pathogens, like your fungal root pathogens, are going to be they're going to have an optimal operation in low to no oxygen conditions. So if you let your soil dry out and there's no more oxygen in that soil, you're going to be eliminating a lot of that species.
Do you recommend folks use a wetting agent every time they water?
No.
No,
it's not necessary. No, it's not necessary. I mean, I don't ever use a surfactant unless it's like IPM foiler, or if your soil's gotten hydrophobic.
Okay, interesting. Yeah, I've heard recommendations to just use it every time because it doesn't really cause harm. It would help the soil in the long run. But so I was just curious on that one.
Well, here's the problem. If you were going to use this, I don't know if this, this is just my thoughts on it, really. If you were going to use a surfactant like yucca or something, or every time, that you're watering, I would assume that at some point, unless you're really letting I water every day, so for me, if I was to use a surfactant every day, it would be a kind of cost effective. It wouldn't be cost effective. It'd be waste of money. But also, what that does is it basically makes water wetter. And when we're in a living soil system, where we want to have the maximum amount of gas exchange, I don't want to create any anaerobic conditions in my soil. So overwatering, or I would think that if you did that constantly over and over every watering, that you could potentially create problems. But it's never something that I personally experienced, because the only time I use a surfactant is for coverage for IPM foilers, or again for hydrophobic soils.
Got it. That makes sense. Okay. Inoculating the soil. So how often should growers be inoculating the soil? I mean, there's some growers out there that 2-3 times a week they're inoculating. They're using Mammoth P, they're using, Great White, then they're adding some recharge. And, can you really go overboard with these? Is there a general recommendation for how often you should be using them?
You could definitely go overboard on your bank, because a lot of those things are expensive, man. You know what I mean? And
great point.
Look, I'll tell you what, guys. Everybody that's listening, I collect data all the time. And I do a massive amount of research. There are so many products out there that are so overpriced or have such small colony forming units that they're going to be ineffective. And then you need to be asking yourself, what's the purpose of this inoculation? If you don't have a clear and concise understanding of what the purpose of, or what metabolites those specific microorganisms do, then you shouldn't buy them, because there's so much misinformation, dude. And I see it all the time, even by professionals. And I have a certain style, and I'm not saying that my style is the only way, because there's more than one way to skin a cat. But when it comes to empirical data that is replicated over and over and over again, I'm looking at specific microbes for specific jobs. I don't use mycorrhizal fungi. I don't use mycorrhizal fungi for a reason, and that's one of the huge ones, right? I will be able to tell all your audience and my audience after my next harvest whether or not there is even an association with an arbuscular or an endomycorrhizal fungi, because there's tests for that now. So I can see if there's an endomycorrhizal that has penetrated into the root itself. What I've seen over and over is that the cost to inoculate with a lot of these things, I don't get any return on it. It doesn't do anything. It doesn't do anything if you have a healthy, balanced soil. In fact, I've read research which has shown in different plants that the symbiotic relationships between mycorrhizal fungi can become parasitic when the plant no longer requires what the benefit is so for instance, let's say your mycorrhizal fungi is releasing phosphatase or a phosphorus solubilizing enzyme into the soil, and that's its job. So this plant releases a photosynthate that is geared for that microorganism to keep it around, and in exchange it'll release the phosphate that the plant needs. Now let's say that's all good in some, agronomic field setting where you're growing a crop in field conditions. But let's take that same scenario and we put that in a system where all your nutrition is adequate and you have adequate phosphate. What ends up happening is the plant no longer requires that once symbiotic relationship to cycle that phosphorus into phosphate, the biologically available form. And so the plant stops releasing that photosynthate. Now this thing we're talking about an organism that has or could have possibly infiltrated every single aspect of this plant's root system, and then that plant stops releasing what it needs. It has control of its whole root system. What is it going to do? It's going to take what it wants because it can. Microorganisms can do amazing things. And Matthew Gates, Sync Angel on IG, who's a great IPM specialist, we talked about, how easily these types of relationships can switch. And something that might be mutualistic can become parasitic very quickly. It's something to take into consideration. Now, we don't have science and all the data for, what I particularly cultivate. However, moving forward, as I'm able to collect more data and more types of tests become available, we'll be able to see how these work, right? I prefer Trichoderma bacillus subtilis combination, and that's because the Trichoderma will colonize the root without causing it doesn't go into the cell itself. Bacillus subtilis will. And the trichoderma will facilitate that. And they have this mutualistic partnership together where they're able to eliminate almost all fungal pathogens. And it's because of trichoderma's high affinity for iron. The metabolite that it produces is the highest iron affinity chelating compound in nature, and that's the sidiophores. What I've seen in organics is that iron is very, very hard to fall into solution in a biologically available form. Ferrous iron, Fe2+. It oxidizes so easily in a pH range from 5.5 to 7 that as soon as you add something like iron sulfate, which should be an immediately available form, it oxidizes into Fe3+. So having a high iron affinity microbe that can reduce, or I guess oxidize, Fe3+ into ferrous iron and make that biologically available, you're going to have a greater impact on that plant's photosynthetic capabilities. So when to inoculate and what to inoculate is, I think, more important. You want to be able to add the right microorganism that is going to do the right thing. I inoculate this product weekly, but I'm also creating a new product because what I've seen is that by using that specific product weekly, that purple non-sulfur bacteria, it's a photosynthetic bacteria, and it's releasing nitrogen into the soil. So if I have adequate nitrogen, I want to stop using that at a certain point. So what I'm doing is I'm constructing a different consortium that's more geared for phosphorus and micronutrient release, as opposed to phosphorus and then getting the added benefit of the photosynthetic bacteria that are adding the nitrogen in.
Really, really good stuff there, for sure. One last thing I want to get into before I let you go. I know you're an extremely busy person. Talk about the rate of reproduction for these microorganisms. So compost teas, often used to extract microbes from compost, and then there's the brewing process where there's microbes are reproducing. What do you know about the rate of microbe reproduction? You can either talk about like the compost teas versus just adding composts into the soil and letting them reproduce there. And do you have any tips for faster reproduction besides what you mentioned earlier?
It's going to vary. It's really going to vary. Something that might be really persistent in soil might not do so well in water. So there's so many different factors when it comes to culturing microbes, and it's really only the strongest microbes are going to be able to survive. So if you're using a complex carbohydrate like molasses and you go and do some compost tea, I wouldn't go, you have a certain temperature range, right, that we talked about. Those are ideal for the production. You also want to make sure, it's so tricky, man. It's such a hard question because like my microbes, I wouldn't oxygenate them to reproduce them. I would solid state ferment them, right? It depends on what you're trying to go for. And if you're just doing compost teas for just a general biology, you're just guessing anyway. So, brew it. Don't brew it longer than 36 hours. That's my advice. 24 to 36 hours is optimal if you're going to do compost or amendment brews. I personally do not use compost teas. I will use compost teas for bioremediation for land, for agronomic settings, but that's because those things are already so deficient. I can add so much into it in any amount, and it's still I could still add more in most cases, because we're building the soil health and fertility. They work great. I think there's a huge disconnect between soil science for agronomic crops, for earth, for farming on land, and then using modified growing mixes. Because me personally, I don't use things like earthworms or crop covers. At scale, it doesn't make sense. What happens when you add earthworms to a system that you're monocropping, it turns all that organic matter into castings, which creates compaction in your soil. So you have this really, really, really light soil that has great gas exchange to this really heavy poop, worm poop, which means you're going to have to add a massive amount of aeration. You're going to have to add a massive amount of calcium amendments to break that open and break that apart. So I was totally disconnected. Now that I'm collecting data and I'm monocropping for just my medicinal herbs, I take a different approach. I'm not trying to do all this crazy stuff. I'm literally just maintaining sufficiency and balance in a system. When it comes to our outdoor and tilling the land and bioremediation and using microbes and compost teas and composting and crop covers, all that, yeah. And the reason is because what we're starting with is something that is not very good. Soil structure's not good, aeration's not good, organic matter's really low, nutrient density's really low. Probably have problems with sodium, so these are the things that we're looking at, and why it's so important to have your soil food web science for agronomic crops, for food crops, for moving towards the future. When I'm talking about something that I've already created, I've mixed the proper aeration, I've mixed the proper nutrient into it. I don't want to do anything else to it. It's almost like I've taken something that would have maybe taken 50 years of bioremediation to get to this point that I have in a bed or a pot. I don't want to change it now. I just want to maintain sufficiency and balance. I will put in the selective target microorganisms that are going to have PGR responses, or that are going to, be there to outcompete any types of pathogens or to cycle nutrients. But I'm looking at target specifics in these modified systems. Now, when we go out of that realm and we're looking at soil systems, we're looking at biodiversity, we're looking at organic matter, crop cover.
Gotcha. Whole different world. Whole bunch of good stuff there for sure. You can get really deep on that level. So awesome. Well, wrapping things up, how can the listeners find you, and what do you have upcoming in the future?
Yeah, so we are ramping up outdoor production on the farm. I'm working on some new microbial products. I'm trying to get a building for bokashi. I've been doing that in my garage forever, and I can't do it here anymore. There's a lot going on. I am always in motion. I am always doing something. You can find me at rust.brandon on IG. You can find a link to Black Label Organics, my farm, Bokashi Earthworks, my corporation, and I also do private consulting too. So
Yeah, for soil samples, right? So if somebody would get a soil sample, they can contact you and you would kind of consult them on that avenue?
yeah, so I work with like very few people actually.
Okay.
And the reason is because of my time and also because I'm usually working with owner-operator farms, and we have a specific goal in mind. I don't typically just do like, oh, hey, somebody wants a test, I'm going to do it. I do, however, I'll help people out, man. It's like I was talking to a guy on Instagram, and he's like, dude, can you look at this soil for me? He's like, I just bought this fresh soil company in Oklahoma. And I was like, dude, like, this is terrible. Like, this is, like, they literally took a bunch of peat and then put some perlite in it and then sold it to you. Like, there's no nutrition in this. It's completely empty. So I DM'd the company and said, hey, I'm a private consultant, and I don't know what's going on here. Either maybe you gave this guy a bad batch of soil, or maybe you guys don't understand target levels, but he can't grow this. He can't grow in this. And this is a small family farm. This guy's relying on this soil, for his livelihood. And it's like, dude, it's frustrating, dude. I hate seeing that, because that dude would have been screwed, but I'm going to help him out. I'm going to get him all dialed in, and, to be able to be productive.
Makes sense. I will leave a link to Brandon's Instagram down in the description section below, so you can easily click on that and give him a follow on IG. Brandon, thank you so much for coming on to the podcast today. It has truly been an honor to have you on this podcast. You have revealed so much information here in this. This is something I'm going to definitely rewatch and have to take notes for on myself, because there's a lot of stuff here that I didn't know, and now I'm a stronger grower because of you. So thank you for that. And I'll let you go, and hope you enjoy the rest of your day.
Thanks, man. It's always a good time when I'm able to help and share, so I appreciate you.